So today I want to talk about the projection operator, and it's not something completely out of the blue, but it's rather closely related to the previous lectures on the unitary matrix, which of course is closely tied to the idea of matrix diagonalization or identifying the eigenstates of a Hamiltonian. So what the mathematicians call the matrix diagonalization in the language of the quantum physicist is to find out what the eigenstates and eigenvalues are exactly for that particular quantum system. So we what we learned last time was that the given some Hamiltonian, which can be actually any n by n Hermitian matrix, you can find this sort of a unitary matrix and perform a unitary transformation on that Hamiltonian so as to bring the Hamiltonian into a diagonal form consisting of only the diagonal numbers, which are real valued, and they're called eigenvalues. Okay, so this is what we learned last time, and we also learned that it's possible to construct the unitary matrix simply by stacking the various eigenvectors, each eigenvector occupying a given column in a n by n unitary matrix, and then its conjugate, Hermitian conjugate, is constructed by flipping each column vector into a row vector and at the same time performing some complex conjugation on all its elements. And that procedure is symbolically written in this way. Okay, so with that, now let me play some trick on this formula which we established last time. And the trick that we perform is simply do the inverse unitary transformation so that now the unitaries act on the diagonal matrix rather than the original Hamiltonian matrix. Okay, so of course this is a self-evident truth, but the point is, why do we do this? Well, the reason why we do this is perhaps most transparent when we write this whole thing out explicitly in the case of a two-level quantum problem, so that the unitary matrix consists of these columns of two different eigenvectors, and the diagonal is a set of two numbers. And for the U dagger, we have these row vectors. Okay, so let's go ahead and perform some multiplication. So this multiplication will give us E1, 1, and then for the second entry we have E2, 2. And now finishing up this multiplication gives us E1, 1, 1 plus E2, 2, 2. Okay, so if the significance of this expression does not immediately become obvious, let me open up a new slide and try to elaborate. So what it says is that given some arbitrary n by n Hermitian matrix, then we can always find a way to express the Hermitian matrix as a sum of such objects. So these are the eigenvalue and the eigenvector coming from the first eigenstate. And then there is this stuff coming from the second eigenstate, etc. So now it becomes a nice collection of things or expressions coming from each eigensector. And to put it in a more transparent fashion, I can write like this, where pi now defined as psi I cat multiplied by psi I bra is a stuff called a projection operator. So why is this called a projection operator? Well, first let me explain the reason behind this terminology. So given an arbitrary state in this Hilbert space, so arbitrary means I can express this state as a linear combination of the various eigenstates of this Hilbert, of this Hamiltonian. Okay, so J goes from 1 through n. And when I act on this arbitrary state with a projection operator pi, so this is one of the many projection operators you can define. And when I act with this particular kind of a projection operator, so now pi will act on this pj. And now let's think about the meaning of this mathematical expression. Since pi is psi I, and psi j, okay, so now suddenly we seem to have this very simple expression, which we know is equal to a canonical delta function, because the way we have set up this eigenstates is that the different eigenstates are orthogonal to each other. Okay, so now using this canonical delta constraint, I can see that this is equal to AI psi I. Okay, so let me explain this process using a simple graph. I take an arbitrary state. Then I process it through something called a projection. So I apply a projection operator. Then the outcome of that process is some constant AI times this particular eigenstate. Since the overall constant does not really matter in defining what the state is, what that projection operator literally does is to select out only that component of the wave function coming from this particular eigensector. And once you have projected an arbitrary state into one particular eigensector, then trying to make a second projection on it will not be able to change the state at all. So then the state continues to be in the same eigenstate. Now, mathematically, that understanding is expressed by the fact that the square of a projection operator is equal to the projection operator itself. And the way you can prove it is if I take the square, then what I'm doing is basically this. but this is 1. So I have this, which is just the projection operator. Now, another interesting thing is if I project onto 2 different sectors at the same time, then let's see what we get. And since we said that these are different sectors, that means I and j are different. So that means this overlap is 0. So the product of 2 projection operators into different sectors is automatically give you 0. Okay, which also makes sense if you just think about it. And the final aspects of the projection operator is that if you add up all of the projection operators for that system, then that ends up being a unit matrix. Okay, so these are the couple of facts that one needs to know about the projection operator. Okay, but what good is it to know how to cast a given Hamiltonian in this new form in terms of various projection operators? Well, first of all, let me introduce an interesting terminology, which is that Hamiltonian written as a sum of projectors with some coefficients. And these coefficients are nothing but the eigenvalues of the Hamiltonian. Such representation is called a spectral representation of the Hamiltonian. Not sure why this word spectral comes into the definition. Perhaps there was a good reason to think that way. But anyway, this is a terminology that's kind of common, and we will also abide by the same notation. Now, first of all, the first immediate good thing about having a spectral representation is that it's very easy to work out the power of a matrix. So when you try to calculate the square of some n by n matrix by hand, then you have to go through this extremely tedious multiplication process n squared number of times, and that's just extremely boring. However, once you have this spectral representation at your disposal, then let's see what happens. It's this is a spectral representation of an H, and since I have to take the square, I'm gonna put another such spectral representation side by side, and that gives me a double sum, EIEJ, PIPJ. But this product of projection operators is equal to 0 unless I and j were equal, in which case I just get back the same projector. So all I end up doing is simply to take the square of the eigenvalue and continue to maintain the same projector as before. Okay? So now the matrix multiplication becomes simply the multiplication of the eigenvalues, which is like, way, way, way easier to perform. Now, applying the same principle, then any nth power of my Hamiltonian will be just the eigenvalue raised to the nth power, multiplying the particular projector. And in this one, I can even define the exponential of an operator as the exponential of the eigenvalue multiplied by the projector. So now it seems pretty easy to come up with a concrete expression for the exponentials of various Hermitian operators, or in the context of quantum physics, exponentials of various Hamiltonians. Actually, this has a very useful consequence for studying the two-level physics, because oftentimes we need to work with this sort of operator, E of I alpha. Let me use a sigma 3 as an example. Okay, and now this is, if you just try to Taylor expand this whole thing, then it's 1 plus I alpha sigma 3 plus factorial I alpha sigma 3 square plus, an infinite series of them. And it's pretty cumbersome to figure out what to do afterwards with it. And now I'm going to show you a very clever way of evaluating this using the projector method. And the way to do it is to introduce these projectors called P3, P plus, which is 1/2 plus 1 plus sigma 3, and P minus, which is 1/2 1 minus sigma 3. Okay, so first of all, why is this a projector? Well, there are various ways of showing this, but maybe the most explicit one is simply by working out its matrix representation. Okay, so when P plus acts on the 1, 0, it returns the same state. But when P plus acts on 0, 1, then it annihilates it. Likewise, when P minus acts on 1, 0, it annihilates it. But when P minus acts on 0, 1, it returns the same state. Okay. So the role of P plus is to do this, where by a plus I mean this state, and by a minus I mean this state. Okay, so all of these things can be understood by writing the P plus and P minus as this and this, right? Because according to this definition, then P plus acting on plus will automatically return a plus, but P plus acting on a minus will automatically return 0. Likewise, P minus acting on plus will annihilate it, but P minus acting on minus will simply return the minus. Okay, so, well, but still, what good is that? Well, first of all, according to the usual rules for the projection operator, indeed, if I add these two projectors, I get one, or one means a 2 by 2 matrix, really, a unit matrix, really. Okay, so if I have a some exponentiated operator like this, I can always multiply on to its right this, because this is basically a multiplication by a unit matrix, which does not change the original content of the matrix. Okay, so now I can write this as two separate terms. Okay, now here is some nice feature. Once you are in this plus sector, okay, but in that plus sector, I know that sigma 3 acting on the plus state is going to give me a plus. So plus is basically the eigenstate of the sigma 3. So what that means is that I can simply replace this operator by its eigenvalue. Okay, since its eigenvalue is 1, then I can just replace this exponential thing by an exponential number. Well, that's actually very good, because you have just removed this cumbersome matrix shaped exponent and replace it by a simple number. Okay, and likewise in this negative eigenstate sector, where sigma 3 acting on this negative eigenstate will return a -1 eigenvalue. You can replace the sigma 3 by its eigenvalue, which is -1, and therefore come out with this, which is identical to the expression in the previous line. Okay, but remember that P plus was just 1 plus sigma 3. Okay, and P minus was just 1 minus sigma 3. So now it's a matter of simple algebra to show that this becomes cosine alpha plus sigma 3 multiplying 1/2 e of I alpha minus e of minus I alpha, which is cosine alpha plus I sigma 3 sine alpha. Okay, so we have this very interesting and simple identity relating the exponential of a Pauli matrix sigma 3 to a form which is nothing but a linear combination of some identity matrix and Pauli matrices, one of the Pauli matrices. Okay, that's very nice. Now, what about the other kinds of Pauli matrices raised to an exponential, like this, or maybe this, or maybe even this, right? This will be the most general kind of Pauli matrices raised to an exponential form. So now can we also bring this to a form that's much simpler, like this? The answer is that yes, you can. And the reason why you can is because we have the all of these coherent state technology at our disposal. So yeah, so this lesson we had in the video a couple of lectures ago now finally comes into play and to help us out through this. The most general kind of an exponential of a Pauli matrix is in fact is this. Okay, so alpha is some number, some real number, and n is a unit vector. It's the same n that we used in defining a two-level Hamiltonian. It's the classical unit vector. Now, let's say we have this exponential form of a Pauli matrix, and we want to evaluate it. Now, the way we do this is, again, by introducing a projector plus n, which is 1/2, and p minus n, which is 1 minus n dot sigma. Okay, so again, why is this a projector? Well, p plus n acting on the coherent state n. Now, this coherent state, remember, is the eigenstate of this operator with plus 1 eigenvalue, and there's other coherent state whose eigenvalue was minus 1. So now let's try to remember these two results and bring them to good use. So p plus n acting on this n state according to this result is n. However, p n acting on the minus n is 0, because then this operator will turn into an eigenvalue minus 1. Therefore, 1 minus 1 will give you 0. Okay, etc. So now, going through these considerations will convince you that p plus n that we define here is nothing but this sort of projector, and p minus n is nothing but this sort of projector. Okay, and when you add these two together, you get, once again, a unit matrix. Okay, so now let's play the same trick as before. I'm going to multiply basically a unit vector to the right, like that, and then separate these into two different terms. Like that. And again, within this given eigensector, n dot sigma can be replaced by its eigenvalue plus 1. And in this eigensector, this n dot n can be replaced by its eigenvalue minus 1. So once again, we have a E of I alpha. Remember, Pn was 1/2, 1 plus sigma dot n. And this phase vector is E of minus alpha now. And with this projector, E1 minus sigma dot n, we have expression very similar to what we had previously, except that we have this more general kind of a Pauli matrix combination sigma dot n. Okay, so now let's remember what we had started, what we had set out to do. We set out to find some simplified equivalent expression for the exponential of the Pauli matrix. And we did accomplish that to find this expression, which is the equivalent of the original exponential form. Now, this formula will come in handy in various contexts of studying the two-level dynamics of a quantum system. So let's try to, familiarize yourselves with these techniques and derivations.